In this session, we will discuss the standard normal distribution. The standard normal distribution is a normal distribution. With any normal distribution, we must have two parameters. Those two parameters include the mean and the standard deviation, where the mean, mu, represents the population mean, or as we have discussed before, the average. And the Greek letter sigma is the population standard deviation. With the standard normal distribution, we also have those two same parameters, mu and sigma. In the special case of the standard normal distribution, the mean is equal to 0 and the standard deviation is equal to 1. Here is the layout of the standard normal distribution. Earlier, we were introduced to the empirical rule, which stated that 68% of the area under the curve lies within one standard deviation of the mean, and 95% of the area lies within two standard deviations of the mean, and 99.7 lies within three standard deviations of the mean. Our z-values represents the number of standard deviations we are away from the mean in our standard normal distribution. So recapping what we said, the mean of a standard normal distribution is equal to 0. And my values, my standard deviation is equal to 1. And my standard deviation values are represented as z-values. The standard normal distribution is like any other normal curve, as mentioned in an earlier video. We see that with any normal curve, we are one standard deviation to the left of the mean, one standard deviation to the right of the mean. And we have the same here. And as you can see, what happens with our inflection points on a standard, any normal curve, there might be a little bit flatter. Or with the standard normal distribution curve, the curve is a little bit steeper. In any way we slice it, the areas under the curve will be equal. And that value that they're equal to is 1 or 100%. You're reminded that when we're looking at the normal distribution, and as we talked about probability distribution, the probability is distributed in the area under the curve. And one thing that we automatically know, or that we can already talk about, is that the probability of being to the left of 0 is 50%, and the probability of being to the right of 0 is 50%. In the back of our book, in Appendix A, Table 3, pages A6 through A7, you'll find the standard normal distribution curve. The key to understanding the standard normal distribution tables is to understand the bell-shaped curve at the top of each page. You have your negative z-scores, meaning that these are the z-scores that are to the left of 0. And on the other page, you have the positive z-scores. These are the z-scores for the values to the right of 0. And when we look at these two tables, we look at the diagram at the top of the page, and we notice the area that is shaded in. As we mentioned before, the area that is shaded in is the probability, or it represents the probability, because the whole area is 1, and therefore any part of it is less than 1, and it's between 0 and 1. Therefore, it is a probability. So, the values on the inside of the table that relates to our z-values, and our z-values are down the left-hand side, which includes the unit value and the value in the 10th place. And then across the top is the value that is in the 100th place. Same here, the values, the unit value and the 10th, and the value that's in the 100th place. So if we're given a z value, and remind you that z represents the standard deviations away from the mean in a normal distribution. If you give me a z value, then I can tell you that shaded area to the left of that z value, be it positive or be it negative. For example, to find the area to the left of a negative z value, we will use the table directly, and we will look at our z value. We'll find our negative z value, and that should be a negative there. We will find a negative z value, or the z value to the left of 0. We'll find it on our table, and we'll read this probability directly. And this probability is the probability the z value is less than that value. When we find the area to the left of a given positive z value, then we look it up on the table and it gives us this value. Now, intuition should tell us that, hey, this value, anytime that I am to the right of 0, or anytime that I have a positive value, then that area under the curve is always going to be greater than 50%. The table gives us the area under the curve to the left of the z values. Well, the question arises, how do I find the area to the right of the z value? So in this case, I'm looking for the area to the right of the z value. So in other words, I'm looking for where z is greater than this value. What's the probability that z is greater than that value? Well, that probability is that area to the right of that value. Well, one way for me to get it is to use the table and find the area to the left of the z value, because the table gives us the area to the left of the z value. I take that area and subtract it from the entire area, and when I do that, it's going to give me this part that's left over. And therefore, in order to get the area to the right of a z value, I have to look up the area to the left of the z value and subtract it from 1. That means that if this z value was anywhere along this line, be it positive or negative, I would do exactly the same thing. Well, you say, hey, Professor, that took a couple of steps. How about if we had a method that would only take us really one step? Well, here's an alternative way of finding the z value, and we're able to use this technique because of symmetry. And we talked about the normal distribution being a symmetric distribution. Because it is a symmetric distribution, if I want to find the area to the right of any z value, all I have to do is look up the negative of that value. To find the area to the right of a negative z value, I will look up that positive, the positive of that z value. Here's something else that can happen with us. We can find the area between two z values. Given that I have a z value to the left and a z value to the right. And in this slide, we Note that our z-value to the left is z1 and our z-value to the right is z2. What we can do is that we take z2, go to the table, find the area associated with z2, and then subtract it from the area associated with z1. And we will get the area between two z values. What that means is that if I do this every time, I can always find the area between two z values, be it that in this case, one z value is to the right of 0 and the other z value is to the left of 0. What if both of my z values were both to the left of 0, or if both of my z values were to the right of 0? Well, the key thing is if I do the same thing every time, then I shouldn't have a problem finding the area between two z values, and therefore once I find the area between those two z values, I find the probability that z is between those two z values. As we stated that the normal probability tables or the z values are entries given to the left of the z value that we come up with. Here is a tutorial to show you how to use the standard normal distribution table. In this case, we want to find the associated row with the sign, units, and tenth portion of the z in the left column. In other words, the first two digits in my z value are in the left-hand column. The third digit is across the top. We move across the top to find the value in the hundredth place, as we mentioned before. Here is an example. In this example, I have a z value of negative 2.84. With this example, I note that I have a negative number, so I'm going to use the negative tables. In this case, I'm going to find my unit value, which is negative 2, and my tenth value, which is 8, along my z column going down. And so I find 2.8, and there is 2.8. And once I find negative 2.8, I'm going to read across to the value that's in the hundredth position, which is 0.04. So most students get kind of confused with the labeling across the top. They say, well, where did you get the 0 from? I'm lost. Well, the 0 is actually compensating for this value because this value is given here. So I'm going to go to the second decimal places, which is here, 0.4, and when the columns meet, the columns and the row meet, this tells me the area under the curve to the left of negative 2.84. That area is 0.0023 or 0.23%. As a final note, as you may note that the table, as far as it goes, is negative 3.49. When we look at areas to the left of negative 3.49, and we're going to continue to use our convention of 4 decimal places, we're going to claim them to be smaller than 0.0001. And on the other end of the spectrum, when we have a z value greater than positive 3.49, we're just going to say they're greater than 0.9999. And that's all we can say because we're only using 4 decimal places. That's the end of this session.